Hello, and welcome to this presentation on space debris mitigation in LEO. My name is Stefan Schelling, and I would like to give you an overview about the potential, challenges, and risks in using high-power lasers for orbit modification from ground. In my talk, I would like to discuss two different use cases for debris mitigation with high-power lasers: collision avoidance and debris removal. As a near-term task, analysis of new collision avoidance technologies is fostered by the UN guidelines on long-term sustainability. As such feasibility analysis, I will give you a short glance on our recent conceptual study named Deceleration, which we have carried out for the European Space Agency. There we have analyzed the impact of laser photon pressure to a debris orbit. Even a deceleration by only 1 mm per second would yield an intract displacement by more than 200 meters within 24 hours after laser operation. Far enough to avoid a collision in case that you have precise orbital data from the debris object. The great potential here is that this would not only protect satellites, but even collisions between two different debris objects could be avoided. The second use case is addressed in the Outer Space Treaty by the demand to ensure sustainable free exploration and usage of space by all nations. In this regard, laser-based debris removal could mean to apply a large delta V to space debris. If we focus here on a large intract delta V, approximately 150 to 250 meters per second would be sufficient to initiate a Hohmann transfer that eventually leads to atmospheric burnup. But as well a radial delta V might be an option for success by lifting the apogee, yielding perigee lowering. Laser-induced force from photon pressure depends on optical surface properties like absorptivity, reflectivity, and transmittivity. And of course, it depends from the incident laser power. As a figure of merit, the momentum coupling coefficient denotes the ratio of force to power, or momentum to laser energy. And for photon pressure, it's in the order of 5 nanonewton per watt. Moreover, the impact of laser-induced heat should be considered. It can be deduced from the object's absorptivity. Finally, the reflectivity can help to assess the risk from back reflections at the debris surface. However, the main threat that one expect here is that it would come from specular reflections at a very flat surface. In sum, force, heat, and back reflections depend on material, laser wavelength, and temperature. Disregarding thermal effects, they all scale linearly with laser power. Photon momentum is rather small when compared to a jet of propellant material. A short high-energy laser pulse can create such a material jet in so-called laser ablation as a consequence of rapid material heating. In laser ablation, momentum coupling is between 3 and 5 orders of magnitude greater than with photon pressure. However, the ablation threshold fluence has to be exceeded, which demands for large laser pulse energies. Of course, not only the ablated material is heated, but there is as well thermal energy that remains at the debris object, resulting in heat accumulation after several laser pulses. The key parameter in laser ablation is the incident laser fluence. However, predictability of heat and momentum from ground is rather difficult, since the related fluence dependencies are strongly nonlinear. In addition to that, pronounced dependencies on material wavelength and pulse lengths exist. In laser ablation, high fluences are needed, which require high energy plus focusing to a small laser spot area in orbit. In many cases, such a small spot is relevant for photon pressure as well, in order not to lose laser power in outshining the debris target. Therefore, it's essential to choose a laser with a good beam quality and a transmitter with a large aperture. Theoretically, this allows to create a meter-sized laser focus in LEO. However, fluctuations of the refractive index caused by atmospheric turbulence can dramatically increase the achievable spot size and prevent successful laser operations. As a countermeasure, the usage of adaptive optics is mandatory for ground-based laser operation. For this purpose, wavefront analysis of light from a laser guide star would enable to anticipate the deformation of the laser beam. Then, in analogy to noise-cancelling headphones, actuators could be used to deform the transmitter optics in a complementary way. On top of that, like the twinkling of the stars, we have beam pointing jitter, as well as some uncertainty about the true debris position, which is presumably monitored by laser tracking. Finally, there might be beam blocking, or at least attenuation by atmospheric molecules, aerosols, or in particular clouds. In the next step, we will analyze laser-induced momentum and heat for photon pressure and laser ablation. Therefore, we choose 4 different types of debris: rocket bodies, payloads, mission-related objects, and fragments. We have employed ESA's DISCOS database to pick some representative examples regarding mass, size, and area-to-mass ratio. Fragments from explosions and collisions, we have additionally used ESA's master model of the debris population and statistics from ground-based satellite crash tests to derive some estimates of the debris properties. First, we take a look at collision avoidance and assume that the debris is on a direct station transit through the zenith. We choose to irradiate it starting with an elevation angle of 25 degrees until a zenith angle of 15 degrees is reached. We use a laser power of 40 kW, a transmitter with adaptive optics, and apply some simplifications, for example, about beam profile and debris albedo. The achieved velocity change is in the order of 10 to 100 microns per second, which at least effectuates a displacement of some meters after 1 day. For collision avoidance, several subsequent laser irradiations would be required, preferably from a station network, as you might have heard on Wednesday from my colleague Heiko Dreyer. Why is the delta V so small for lightweight targets? The reason for the underperformance of momentum transfer here is that lightweight often means small. But on the other hand, we have a large beam diameter. We can detect the related large outshining losses for small debris when we compare our results with the estimate using full laser power. So what remains to obtain a large delta V is to use a multitude of laser passes, or to simply increase the laser power if available. In our study for ESA, we have chosen 40 kW as what we deem realistically to be feasible within the next years. But whatever comes on top would help by simply linear scaling the delta V with laser power. But what about laser ablation? For the simulation, we have used experimental data on momentum coupling and laser ablation of aluminum and steel. We have found that if the laser pulse energy is too low, the debris trajectory will not change at all, since the threshold fluence for laser ablation, which is in the range of 1 to 2 joules per square centimeter, is not exceeded yet. More than 50 kilojoules would be required here in order to cause laser ablation on the employed debris materials. Note that other materials have different ablation thresholds and other laser configurations in terms of wavelength and pulse length to change the picture as well. If now the threshold for laser ablation is exceeded, collision avoidance can be undertaken instantaneously within a single laser pulse, instead of after several station transits using photon pressure. Admittedly, this is no straightforward technology solution, since lasers with such a large pulse energy are not available commercially off the shelf. But when we take a look at research facilities, we find that in fact such laser pulse energies in the order of 100 kilojoules are conceivable and could, for example, be achieved by beam combining of several laser beam lines as used for inertial confinement fusion. In principle, one could also operate several of those combined beam lines subsequently after each other, for example with a pulse repetition rate of 1 Hz. Then, at the same average laser power we have just had for photon pressure, momentum coupling would be again 3 to 4 orders of magnitude higher using laser ablation. Here we finally come to a delta V in the order of meters per second. Hence it's conceivable that after a multitude of transits above such a laser station, the overall delta V will yield parity lowering, being sufficient for debris removal by atmospheric burnup. What about heat in laser-based orbit modification? If too much heat is acquired from debris using laser operation, one might run the risk of target meltdown or droplet formation. Heat accumulation has to be assessed carefully to avoid fragmentation from thermal stress or detonation of residual stored energy. It's obvious that for collision avoidance using a single laser pulse instead of several minutes transit above a photon pressure station, it's beneficial to use laser ablation in terms of heat accumulation. But the risk of fragmentation due to shock waves has to be assessed for laser ablation in general. Therefore, the risk assessment of target heating is the most complex in the case of repetitive ablation for debris removal. When we review our findings on laser-based orbit modification, what do we have to consider for operational safety? First of all, one has to be aware about everything that could make this endeavor a harmful activity. The lasers are operated here on a power level which is several orders of magnitude beyond the maximum permissible exposure for the human eye, which in particular has to be taken into account in safety measures for air traffic and the public on ground. But as well, active satellites in the foreground or in the background of the debris target have to be protected. Moreover, laser-induced heat shall not endanger the target's integrity, and momentum transfer uncertainties have to be taken into account before clearance for orbit modification. The employed technology can to a great extent be considered as dual-use technology. And in particular, the risk of weaponization should be addressed by searching ways for global governance for the peaceful usage of high-power lasers in space. Laser-based orbit modification has the potential of ground-based access to a multitude of space debris objects. Photon pressure is rather a near-term option using commercially available lasers, but it has the drawback of very small forces, suitable rather for collision avoidance only. Laser ablation is much more powerful, exhibits a better ratio of residual heat to applied momentum, but it's much more complicated to predict. The most crucial technological challenges here might be turbulence compensation for high-intensity power beaming and debris reconnaissance for the assessment of thermal integrity. High-power laser usage requires to carefully address several operational risks, ranging from unintended dazzling to the threat of weaponization. But beyond all open questions, laser-based debris mitigation appears to be worth the effort of research, validation, and development. It offers a unique potential to contribute to space debris mitigation on a grand scale. Therefore, joint efforts should be undertaken to make it less futuristic than the onset of an exponential evolution of space debris itself. Thank you so much for your kind attention in joining this presentation. I'm looking forward to your questions and comments.